Okay. Okay. Think we can go. So let me share my screen so that I can see. Okay, please can you see my screen? Please can you see my screen? Hello, please can you see my screen? Okay, thank you.
Yes.
Okay. Yeah. Okay, so before we went for the break, we solved the first question, but because the first one we couldn't get proper recording, I'll start from the question again. Okay, so per phase equivalent is the per phase equivalent circuit of a 4 pole, um, 415 volts, 50 hertz induction motor may be approximated to a magnetizing inductance of 600 milliamps, a rotor resistance of 0.453 ohms. The rated speed of the machine is 1480 revolution per minute. Calculate the rated output power, the rated torque, and the rated current. Okay, so let me go in. What up? Okay, so let me pick a pen. Let me divide this into two. Okay, so the parameters are, first we have the pole pair. The pole pair will be equal to 2. Then we have the phase voltage. We are assuming it's star connected, so that will be 415 divided by root 3, which will be 240 volts approximately. Then the frequency of the supply voltage is 50 hertz, right? Okay, so the motor may be approximated by a magnetizing inductance of 600. So that means we are ignoring the rotor resistance and the leakage inductance. So this is a magnetizing branch. Then the rotor also by just the resistance. That means we are ignoring the rotor um, leakage inductance. Okay. So the supply here is 240 volts. This place is 600 millihenries. Then this is 0.453 ohms. Right. So we are to determine the rated output power. We know the rated output, that's the P mechanical or P naught, is equal to 1 minus S all divided by S times IR squared, IR squared times R, right? Yeah. So we have this. Now we need to determine the slip. Okay, so we know the slip is equal to omega E minus omega R, right? Omega E minus omega R all divided by omega E. And you can, we were given NR, right? The speed in revolution per minute, that's the rotor speed, to be 1480. We can find NS to be equal to what? 60F divided by what? Small p. So the NS is going to be 60 times 50 all divided by 2. And the synchronous speed in revolution per minute will be 1500 RPM. right? So either you convert this NR, which is 1480 RPM, either you convert this and this to rad per second, then you use it, or you can, for the sleep, you can use this one straight away. Is that okay? So I don't need to convert this to rad per second. I will just do NS minus NR, all divided by what? WE, uh, or over NS. Okay, so this is going to give me 1500 minus 1480, all divided by what? 1500. So LC will give you 0.0133. Sleep has no unit. Okay, then I can find my power. But to find the power, I need what? The current, the rotor current. So the rotor current is given as what? It's given as V1 divided by RR on what? S. So this will give me 240 divided by 0.453 divided by what? 0.0133. So IR will give me what? Okay, it will give me 7 point, I think 064 amps. Okay, you can check it out. Okay, so if I get this, now I can find what? The P mechanical or the output power. So P0 should now be equal to what? Okay, 0.46, sorry. So 0.46 amps. Okay, so this should now be equal to 1 minus 0.0133, all divided by 0.0133 times I squared, so 7.046 squared times the resistance, which is 0.453. Okay, this is the power per watt per phase. If you were in the last meeting, we saw that this is the power per phase. Okay, so if I want to get the total power, PT should be equal to 3 times what? The power per phase. Power per watt per phase. Is that okay? So to get the total power, you multiply this by 3, and this should give us what? 5.031 kilowatts. Okay, so now I have the power. We know to find the torque. The torque is equal to the mechanical power, the total mechanical power divided by what? The speed of what? The rotor. Okay, we have the total mechanical power and we know the rotor speed. So this is going to be 5.031 times 10 to the power 3, all divided by the rotor speed is 1480 RPM, and to calculate torque in Newton meters, your speed has to be what? Rad per second. Okay, so to convert this to rad per second, we multiply this by what? 2 pi on 60. So I can send the 60 to the top here, and this will give me what? This will give me 32.46 Newton meters. I hope that makes sense. Okay, then the second part of the question says, now let's move to the second part of the question says, now let's move to the next part of our problem. The induction machine we've been working on feeds a load which can be characterized by what? The equation TL equal to 5 plus 0.05 times what? The speed. Is that okay? Okay. So remember, okay. Remember when you are designing a drive for a certain load, you have to make sure that your motor or your drive meets what? The characteristics of the load, or the load meets the characteristics of the drive, whatever it is. Okay, make sure their characteristics what meets. And at the point where, so most of the time You draw the motor characteristics, you draw the load characteristics, then you see where they meet. That will give you uh, the point at which you can operate it. Is that okay? Sure. So it is the load characteristics. So where omega r is the mechanical speed. Remember, yeah, omega r is the mechanical speed in what? Radians per what? Second. Calculate the speed and torque developed when the stator voltage is reduced to what? 380, then 250. Was still at what? A frequency of 50 hertz. So we want to keep the parameters the same. The only thing we want to do right now is just to change the voltage. We are not changing the frequency, we are only changing the voltage. Yeah. Okay. So if that's the case, we know TE is equal to what? 3 VI squared times RR times what? S omega E times what? The pole pair. We derived this formula in the first session. So if you're not here for the first session, this may look weird to you. Over omega E squared times what? RR squared, right? So then this here will cancel this, the square here. So then this should be equal to 3v1 squared uh, times the pole pair times what? Omega slip, because s times the synchronous speed is the omega slip, or the slip angular frequency, all divided by what? Omega E squared times what? Just the resistance. Okay. So at equilibrium, TE should be equal to what? TL. So then we can say TL should be equal to whatever we have here. Now the voltage has changed, so now we need to find a new phase voltage. So now the new phase voltage should be equal to 380 divided by what? Root 3. And this should give you what? 219 point something. 380 on root 3 give you 219 point something. So then we are now going to have 3 times, yeah, point 39, so 0.39 volts. So 3 times 219.39 squared, right, times the pole pair, which is 2, times the slip frequency. Slip frequency is what? Omega slip is equal to omega E minus what? Omega R. So then that's going to, omega E is what? 2 pi times what? The frequency, which is 50, minus omega R. All of these divided by what? The square of the synchronous speed, which is, or omega E, which is 2 pi times 50 all squared times 0.453. Okay, so then TL is equal to, this place will give us 6.46 times 100 pi minus omega R. If you expand it, so now we know what TL is, 5 plus what? 0.05 omega R should be equal to what? 2029.256 minus 6.46 omega R. If you group like terms, you are going to have 0.05 omega R plus 6.46 omega R should be equal to, so 2029. So this will give you 2024.256. Then if you make omega R the subject, you get omega R to be equal to 310.95 rad per second. Okay, but you are supposed to look for what? The mechanical speed, not the electrical speed, because this is the electrical speed. So then the mechanical speed is equal to the electrical speed divided by what the pole pair. So this will give you a 310.95 divided by what 2. So then the mechanical speed should be equal to what, 155.475 rad per what second. I hope this is making sense. Okay, so now this is the speed in rad per second. But if you want it in revolution per minute, so let me call it Nm. This will be 155.475 times what 60 on what 2 pi. So this is going to give you the speed in what revolution per minute. So this will give you what Nm will be equal to what 1485 rpm. Okay, so you have to find the speed and the torque. So now you just come and put this value over here. Where is it? To find the torque, you already have the torque equation. So now the torque should be equal to what? 5 plus 0 0.0, 5 plus 0.05, right? Times 310.95 rad per second. So this will give you the torque you are looking for. Okay, so that should give you 20 point something. Okay, then you use this same method to find when you reduce the line voltage towards 250 volts. So you just have to find a new per phase voltage and go through it again. I hope you get it. So any question? One person is inside. Okay. Yeah, so that is for the first question. So let's go to it. Okay. So the next question, which is question 2. Okay. So question 2. A 4-pole 3-phase cage rotor induction motor has the following parameters referred to the stator side. So you have RS, you have LS, you have LO. LO is the magnetizing branch inductance. You have LR, you have the rotor resistance. All the values are what? Per phase values. Assuming a star connected machine, the machine is fed from a 415 volts line. So that's the line voltage, 50 hertz of light. And the slip is what? 4%. Ignoring the effect of what? RS. Okay, so this one is negligible. This is negligible. This is negligible. Okay, no, this is not negligible. So then this is negligible. Determine what the rotor speed, the torque, and the power dissipated in the rotor resistance. That's the P slip. Is that okay? So let's go back here. So I can erase this. I wish I could add another page, but Jamboard was giving me issues. Okay, so now for the parameters, so your motor circuit would have looked like this, right? Then you have the magnetizing branch, then you have LR, then you have this. Okay, this place will be what 240 volts. But the question says we should we should ignore this, and ignore this. So then our circuit is going to reduce to what? This. It's just going to reduce to the one we solved earlier. Okay. So we know this resistance to be what? We know this resistance to be 0.2. So this will be 40 million henries. Okay, so we are supposed to determine the rotor speed. Okay, so we've been given the slip, but we're not given the number of what pole pairs. But if we have a slip of what, our slip is 40%, so we know synchronous speed to be equal to what, 120 F divided by total number of poles. So let's take it 2P, where P is the pole pair. Is that okay? So we have this, and our frequency is what? Our frequency is 50. So we have 200 this times what? 50 divided by what? 2 times what? Pole pair. So in this question, we are going to assume that the total number of poles is what? The total number of poles is 4. So then our pole pair is what? 2. And if that's the case, then our synchronous speed should be what? 1500 RPM. Then if that's our synchronous speed, and we know the slip to be what? The slip is 4%. So 4% is 0.04. That should be equal to what? 1500 minus what? Omega R divided by what? 1500. Okay, so then 0.04 times what? 1500 should be equal to 1500 minus what? Omega R. So then omega R should be what? Calculator here. 1500 minus 0.04 times 1500. Okay, so that would be our speed. So that would be 14. Okay, please give me a second. Let me punch it. Okay, so this should give you 1440 RPM. Okay, so then that should be the speed of the motor. Then the next one is for us to find the torque. Okay, so to find the torque, I can determine IR. So if I have IR is going to be what? V1 divided by RS over S. So this is going to give me what? 240 divided by 0.2 divided by what? 0.04. So this should be equal to, so this should be equal to 48 amps. So then if this is equal to 48 amps, I know that I can find my total mechanical power. That should be equal to 3 times 1 minus S all on S times IR squared times what? RR. So this should be equal to 3 times 1 minus 0.04 all divided by 0.04 times 48 squared times 0.2. Is that okay? So this should give me, so then the total mechanical power, PO or PMEC, whatever you call it. So the total mechanical power should be, okay, we are still punching. So then the torque should be equal to the total mechanical power P mech, right, divided by what? The mechanical speed. Okay, so this should be equal to, okay, so this is 33.178 kilowatts. Okay, so we should have 33.178 times 10 to the power 3 time, all divided by, we saw that the speed is 1440 times what, you have to convert it to radians per second. So then the at the top here we have 60. So then our torque should be equal to what? Okay, so this should give you 1.38, 1.382, sorry, this should give you 220, sorry. So this should give you 220 point 02 Newton meters. Yeah, then the next question says what? So after finding the rotor speed, you find the torque. Then now you find the power dissipated in the rotor resistance. In a morning session, we said the power dissipated in the rotor resistance is equal to a P slip. And P slip is equal to what? IR squared times what? RR. So then this should be equal to a 48 squared times 0.2. Then this times 3 because this is P slip per phase. Okay, so this should be multiplied by 3 and this is equal to 1.382 kilowatt. Okay, so that's for the question 2. Okay, so yeah, we are done with the first part. Now there are other babies there. Yeah, so you can see the answers over. So this is the speed, this is the torque, and this is the power dissipated. Now the question says the supply voltage is now reduced to what? 346 line voltage, but the load torque remains constant, making the same assumptions. That's ignoring whatever we ignored here. Determine the rotor speed and the power dissipated in what? The rotor resistance. So we are now going to determine the speed. Okay, so the only thing that has changed here is what? The line voltage, right? But the torque is constant, so we are still maintaining a torque of what? 220. So we know that what Te is equal to what? 3V1 squared, the pole pair times what? The pole pair, okay, we take this R out because it will cancel the square down there. Then we have what? Omega slip. Is that okay? All divided by what? Omega E squared, then RR. Okay, so now our V1 phase will be equal to what? What's the voltage? 346. So 346 on root 3. So that's 199.76. So that's approximately 200 volts. So then we are going to have this should be equal to what? 3 times 200 squared times what? The pole pair, which is 2, right? Then this omega slip, remember omega slip is equal to what? S omega E. So then we are going to have times S. times what? Omega E is what? 2 pi times 50. All divided by what? 2 pi times 50 squared. 2 pi times 50 squared, then RR. Okay, the square here will cancel whatever we have here. So then this place we are maintaining what? 220 should be equal to what? What is this? 3 times 200 squared times 2 divided by. Okay, this place should be multiplied. How did I write RR here? This place should be 0.2. So times 0.2. Okay, so this should give me 220 equal to 3819.72 S. So then my sleep should now be equal to what? This divided by this. So that would be 220 divided by whatever we have there. And this is going to give us 0.05, 0.058. Okay, so this is now our sleep. Then if this is now our sleep, then we can find what? The rotor speed now. Because we know sleep S omega E is equal to what? Omega E minus what? Omega E minus omega R, right? So omega R is equal to 1 minus S omega E. No. So this should be equal to 1 minus 0.058, 0.058 times 1500. That will be our omega R. So omega R should be equal to what? 1413 RPM. Okay, so that's omega R. Now, what else are we supposed to find? So after find the speed, we are supposed to find the power dissipated now. Okay, so now that we have a new sleep, IR will now be equal to what? Now voltage is going to be 200 divided by 0.2 divided by 0.058. So what's our IR? So 200 times 0.058 all divided by 0.2. So now our current will be 58. So now P sleep should be equal to 3 times IR squared, which is 58 squared, times what? 0.2. Okay, so that should give you like uh, 2.0 something or 1.99 depending on how you go about it. So 2 kilowatts. Okay, so you can see that just changing the voltage, the line to line voltage from 415 to um 346 or whatever it is, we have what? I think we've actually increased the losses from what? Just changing this voltage by this, we've increased the losses from what, 1.38 to what? 2. Is that okay? Yes. So that's what happens if you do for induction motor, if you do a variable voltage without varying the the frequency as well. Okay, you are just going to increase the losses. Okay, even though this has changed the speed, you can see that the speed has changed from what 1440 to what to so the speed has reduced. You have actually reduced the speed. But in reducing the speed, you've increased what the sleep, and increasing the sleep, you are going to increase what the p sleep. I hope that makes sense. Okay, so then the following one, which I'm not going to do, you can do that. The next one says discuss whether neglecting the RS, LS, and LR leads to significant errors in what calculations. So that means now you have to do the calculation without ignoring what the things you ignored. So then you have to bring back the parameters we ignored here. Of course, it's going to introduce some error. Is that okay? It's going to introduce some error, but I'll do something similar in another question, so I'm not going to waste my time here to do. So you can see, okay, for here it didn't change the speed, but and you see it has changed the torque over here. So that means this should have been the actual torque 199 Nm, but because we ignored some of the parameters, we got to 220. Then this place we should have gotten on 1.25 if we hadn't ignored. I hope that makes sense. Okay, sure. Let's go to the next question. Okay, so it says what? Calculate the starting current for the machine described in question 2. When supplied from a 415 volts 50 hertz supply, the same machine is connected to what? A variable voltage. Okay, so you are supposed to calculate the starting current for the machine described in question 2 when supplied from a 415 volt 50 hertz supply. So so we need to calculate that one. So it's simple. Okay. Okay. Sure. So this question, depending on what you want, this one, did you say we should maintain the same assumption? Let me read the entire question. The same machine is connected to a variable voltage, uh, variable frequency supply, which is controlled so that the magnetizing current is maintained constant. The minimum frequency step of this inverter is what? 1 hertz. Calculate the starting current for this drive system. Okay, so first of all, this is our system.
Caitlin,
I'm the one, it's not Kirkland. Okay, so this is the actual circuit, but just that the other questions made us uh, told us to make some assumptions. So this is the actual circuit, right? Okay, so this RS, this is LS, this is um this LO, this LR, and this is what RS. Okay, on S. Okay, so this is what we have. There are two ways you can go by it. You can make assumptions. So if the question says you can make assumptions but state your assumptions, then you can say that okay, you are assuming this branch. The solutions in the slide they assume this branch. So we are looking at the first part of the question where we are analyzing this. So the line voltage is for 200 and the line voltage is 415, so the phase voltage is for 240 volts. Okay, so the solution in this slide they actually ignored this. Then if you ignore this, then the circuit will reduce to what? Then it's going to reduce to this. Then you have 240 volts. Okay. Then so you have to say that okay, you are ignoring the magnetizing branch. Maybe you are saying that okay, the current that goes here is small, whatever. So if you ignore this, then you have all this in series. Is that okay? You're going to have all this in series. So let's do that method. Then let's look at when we don't ignore it. So if we ignore this, then this is a resistance, this is a resistance. Okay. Then the total impedance will be the sum of the odds. So it's going to be what? Rs plus J omega E, Rs plus J omega E Ls plus Rs RR on what? S plus what? J omega E L J omega E L what? R. But if you read the question very well, the question says what? It has starting. Okay, it has starting. Then if at starting the rotor is not moving, right? The rotor is not moving, and if the rotor is not moving, then your slip will be equal to what? 1. Okay, so then your Z total is going to be what? Rs plus what? RR, which is going to give you what? 0.2 plus, I think 0.1. So we are still using the parameters for the question too. So then plus 0.1, then plus J, you sum the inductances. So this will be what? Uh, you have 40 milliohms. You have 1 milliohm. This one is also 1 milliohm. So then that will give you 0.001. Right? That's 1 milliohm in what? Millihenries in henries. Okay. Then you factor omega E out. So then this times what? 2 pi times what? 50. So this will give you your Z total. And that's going to be what? 0.3 plus or J what? So that will give you 0.628, right? So this will be your Z total. Okay. So yeah, if you take the magnitude of this Z total, if you take the magnitude of this is going to be 0.696 ohms, right? 696 ohms. Then you can find the current that is flowing here. So the current is just going to be what? So then your starting current, right, Is should be equal to what? 240 divided by 0.696, and this should give you what? This should give you 344.83 amperes. Okay, so this solves the first part of the question. So you have 345 over here. So now we've just solved up to this point. Okay, that's the starting current for the machine described in question 2 when supplied from what? A 415 volt 50 hertz was supply. If you want to solve it, if you want to solve it without neglecting this, so if you want to solve it this way, then you have to find the total resistance. So what you need to do is you find the equivalent impedance over here. Then this will be what? In parallel with this. So you find their parallel combination, then together they will be in series with this. So in that case, for this side, you are going to get what? You are going to get so for this part, let me call it ZR. For the root 2, you are going to get 0.2 plus J, then J 0.001 times what? 2 pi times 50. Okay, that will give you Z what? R. It will give you 0.2 plus a certain value. Okay, then you come here, the value you get here, you put it in what? In parallel with this. So the ZO, so you find ZO will be equal to J omega E. So omega E will be what? So 2 pi times what? 50, then times 0.04. So that's 40 millihenries. Then when you get this, you you come and let me call it Z total 1 should be equal to what? This in parallel with this. So that will be Z R Z O divided by what? Z O plus what? Z R. Then whatever you get here, the total impedance will be equal to what you get here. So let me call that one ZS. So ZS will be what? RS plus what? J 2 pi 2 pi times 50 times what? 0.001. Is that okay? So that's ZS. So then your total impedance ZT should be equal to ZT1. Oh, sorry. ZT1 plus what? ZS. Then now if you get this total impedance, you now come and find your IS as what? 240 divided by 240 divided by the Z total. Okay. I think when I did it, I had 349 on an angle of what? Minus 65 point something. Okay. So the magnitude here will be what? 349, which is quite close to what? 345. And it is not the same because here you are not neglecting what? This. Okay. Sure. So that's how you go by it. Then let's go to the next part, the other part of the question. So it says that this same machine is connected to a variable voltage, variable frequency. I don't know why this question came here. This question shouldn't have been here because there's a principle we are going to look at next, which will help you solve this question. So because we've not done variable so far, we've just looked at variable voltages. Sorry. Okay, so for the variable voltage, variable frequency, we said that what Im should be kept constant at all times, and we know Im is equal to what? Vm divided by I think J omega E L what? Lo. Okay, let's call it this way. We said that we don't want this Im to change. Is that okay? We would like to keep this Im what constant. Therefore, the Vm, because this is a constant, the Lo is a constant. This Vm here and the omega E should change in the same proportion, such that if I increase Vm by 2, so so if the new value of Vm is equal to 2 Vm, then the frequency or this speed over here should now be what? J2 omega E what? Lo. So that at all times the proportion here will be what? The same, or they will increase in the same ratio. Is that okay? It's a principle we are now going to look, but the question is here, so we need to look at it. Okay, so that's for every. So now we are varying voltage and we are varying what? We are varying frequency. Is that okay? So that's the variable voltage, variable frequency drive we are going to look at. Okay, so then what? So now we are going to look at this same circuit. This is at 50 hertz. We are going to look at this circuit at what? 1 hertz. So let me get the eraser. Let me clean this part. Okay, so from what I explained here, for variable frequency, variable voltage, Im should be constant at what? At all frequencies. So that means Im at 50 hertz should be equal to what? The magnetizing current as what? Or Im at what? 1 hertz. I hope that makes sense. So now, first, the system was actually. So what we are going to do now, we are going to look at the system at what? 1 hertz. The system at 1 hertz. Just use 1 hertz to find the inductance over here. The reactance over here. The reactance here is going to be very small because did I actually do this? LS RS. So the inductance here is going to be very small because it will be what? 2 pi times what? 1. Is that okay? It's very small. So we are going to ignore this. Is that okay? We are going to ignore this. So our circuit reduce. You can still go ahead and analyze without ignoring it. I've showed you how to do that. So we are going to ignore this. Then uh, we will ignore this as well. This one to eight eight inductance is what 0.1 millihenries, and we are now going to look at it at what 1 hertz. So it's going to be 2 pi times 1 times what 0.001, and this is going to give you a very small value. So we are going to ignore that one as well. Okay, so then our circuit reduces to this. So if our circuit reduces to this, we said so what will be Im at 50 hertz? Im at 50 hertz should be equal to this voltage 240 volts divided by what? The impedance here at 50 hertz. So okay, let me write it well so that you know what we are finding. So Im at 50 hertz at 50 hertz should be equal to what? 240 volts divided by what? 2 pi times 0.04 times what? 50. Okay, so this will give us what? 19.099 amps. 240. Okay, so we are going to get this current. So then Im at what? 50 hertz. Im at 1 hertz should be equal to this. So Im. So okay, let's find Vm at 50 hertz. Vm Vm at 50 hertz is going to be what? Im Xm, right? So this should be equal to 19.099. Do we need that? I'm not sure we need that voltage. Is that okay? So then, what will this value give you? 2 pi times 0.04 times 50. Sure. Okay. Okay, so I think we don't need this. Okay. So now, since it's the same, so that means IM at 1 hertz should also be equal to 19.099 amps. Okay. Then what will be VM? What will be VM at 1 hertz? 1 hertz. That should be equal to what? The current at 1 hertz, which is what? 19.099, right? Times what? Now that the frequency has changed to 1 hertz, the reactance we are going to see here will what? Change. So you see that VM will change because, okay, let's find this VM at 1 hertz first. So this will give the reactance here will be what? 2 pi times what? 1 times what? 0.04. So what will be VM? That will be 4.8 what? Volts. Is that okay? Now let's look at something. Do 19.099 times what? 2 pi times 50 times 0.04. 0.04. So this VM at 50 hertz. So that will give you a 240. Okay. That will give you 240 volts. Okay. So you can see that now we've changed VM from 240 to what? 4.8. The same way the we've changed the frequency from what? 50 hertz to what? 1 hertz. Is that okay? So we have we varied the voltage, and we have what? Varied the frequency as well. Explain that one. Okay. So you can see that now the these ones have changed. The voltages have changed and the frequencies have changed, but they've changed in what? The same proportion. Let's do something. Let's do okay, so 50 hertz divided by 1 will give you what? 50. Let's do 240. 240 divided by what? 4.8. That will also give you a 50. So you can say that the voltage and the frequency have changed in what? The same proportion, 50-50. Therefore, the IM will remain what? Constant. I hope this makes sense. Okay. If you have a question, you can put it in the chat. If only there's somebody in the meeting. Okay. So now that we have this VM at 4.8 voltage, volt, we know the current to be what? 90.09. Now we can find the current in here. Okay, we are still at all. Starting. So now the voltage that will appear across the rotor resistance is going to be what? This 4.8, not 240. I hope this makes sense. Okay. So then we are going to have IR to be equal to 4.8 divided by what? 0.2. And this will give us what? Is it 24? No. Uh, 4.8 divided by 0.2. Okay, so yeah, 24 volt, 24 amps. So then the starting current IS should be equal to the vector sum of these two currents. So I'm going to have 24 squared plus what? 19.099 what squared. Square root of this. So that's going to give me what? 30.672 amps. Yeah, so that will be the starting current in this case. Okay. So any question? Let me see if there is any question. Okay. Hey, I've stopped screen share. Maybe that's why it left. But they should have told you. No, no, this one. This one is recording on screen. Recording on screen. Okay, so that is for this question. You have to solve this one too. Let me solve this one. The last one I won't solve it. You have to go to this place. Okay. So question 4. So the machine described in question 2 is fed from a variable frequency drive. The machine described in question 2 is fed from a variable frequency drive voltage supply. This supply introduces a voltage distortion when the modulation frequency is what 50 Hz, such that a fifth harmonic with an amplitude of what 4% of the fundamental appears in the stator voltage. So that means aside the fundamental frequency voltage, stator voltage, there is what a fifth harmonic one whose magnitude is what 4% of the fundamental. Calculate the increase in what rotor copper losses. So we said that whenever you have harmonics, they cause what the increased losses. Okay, so now we are going to calculate the increase in the rotor copper losses when the drive is operated at what rated torque. Is that okay? So first of all, we need to find this um, stator harmonic voltage. Okay, so the stator harmonic voltage. So I'm going to call it. Let me go back to my one pin. Okay, so I'm going to call it stator voltage, stator harmonic voltage. The question says, well, it's 4% of the fundamental. So that's going to be 0.04 times what uh, the fundamental is 240. So 240. What that all is. Let me go back to my one paint. Say paint, one paint. Hmm? Yeah, you can check it. Okay. Okay, so VSH, which is the stator harmonic voltage, is what 4%, so 0.04 times what 240, and this is equal to what 9.6 volts. Is that okay? But what is the rated? Okay, so now we need to find the rated speed. Is that okay? So we are still taking parameters from the question 2. Is that okay? So our rated speed, which is equal to omega r, should be equal to what? S omega E. Remember, this is also equal to what? Omega E minus what? Omega R. Oh, oh no, no, no. I'm coming. That's a big lie. Why did I make this thing so big? So times 240 volts. Okay, this is 9.6 volts. Exactly. So the rated speed is equal to what? Omega R. Exactly. And omega R is equal to what? Omega R should be 1 minus S, I think, omega E. Is that okay? We are still picking parameters from the question 2. So let's go back to question 2. What's the sleep of what's the sleep we're giving? The sleep is what? 4%. Okay. So if the sleep is 4%, what will be the rated speed of the motor? It's omega R equal to 1 minus 0.04 times what? There, this one is 1,500. Remember. So omega R is equal to what? I think it was 1 4 something. 1440 RPM. That is a rated speed. Okay, so that's the rated speed. Let's go. We are at question 4. Okay, so now our this one has changed. Our sleep has changed. Our sleep has changed not because our omega R has changed. We are now looking at the effect of the harmonic voltage, and it says that it's a fifth harmonic. If it's a fifth harmonic, for the fifth harmonic voltage, its synchronous speed, the flash is going to produce, the synchronous speed will be equal to what? 5 times that of what? The fundamental one, because if you are going to have a 2 pi f times what? 5 times what? 50, because that one is going to have a frequency of what? 250 hertz. Is that okay? So then, with this same, the question says at what? Rated torque. So at rated torque, we have what? Rated speed. So then, what will be our sleep then? Our sleep will now be equal to what? The sleep will be equal to the new omega A, which is what? 5 times the fundamental one, 1500, minus what? Our rated speed. So 1440, all divided by what? 5 times 1500. So what will be our new sleep? So that will be 0.083, right? So you can see that from this, like 8.3%. So the sleep has increased from what? 4% to what? 8.3%. I hope that makes sense. So that if your sleep has increased, definitely your this one should increase. Definitely your losses should increase. So now we know that our P sleep is equal to IR squared times what? Times this. Okay. But what is IR? IR is equal to what? V1, right? V1 divided by what? IRR divided by what? IS. So now the voltage we have over here, we are looking at the voltage, the harmonic voltage. So that's going to be on 9.6 divided by, this is what? 0.2 divided by what? 0.8 or 0.083. So this should be equal to what? So 3.984 amps. So then P slip should be equal to three. Okay, 3 times 3.984, because what we have here is what per phase. So 3 times 3.984 times what 0.2, and the answer is what? Okay, this should be squared. What's the slip? How did we get for the slip? 5 times 1500 minus 1440, all divided by 5 times 1500. Okay, so the slip should be 0.808. Okay, so this place should be, this current will change. So 0.808. Okay, so 38.784. So 38. Okay, let me clear this. 38.784 squared. So 902.5. 902.5 watts. Okay. Yeah, so that's for the question 4. So try the question 5. It's not difficult. You'll be fine. Okay, so now the next one is the variable speed induction motor drives operation from a voltage source converter. Okay. Stop.